Alright, ladies, chapter 6. Here we're working with trigonometric identities. We're going to be spending 8 hours on this one here. And just some keynotes here. We have 6.1, 6.2 quiz is in a couple of days. We do have our assignment and then a test. We have one keyword that we're looking for here, which is the trigonometric identity. And this is a cheat sheet for you guys. You guys can use this into your, for your tests and quizzes. You can just remove this page or, do whatever you want with it. And for your final, the departmental will give you all of this except for these nice special angles and their exact values. They're just ones that we pulled from the unit circle. They're just in one organized place, so it'd be really nice to see. So you guys can always refer back to this, use this in your quiz, your test, your assignments, do whatever you want with it. And hopefully that'll be a nice way to get you guys started. And one exciting announcement, I bought myself a $120 writing tablet, so I can now write on my Word documents. This is like the most exciting thing ever, or, well, of the day. So we'll see how this goes. It'll be really interesting. So we'll see how it works. Hopefully it'll be better than me typing. Alright, so section 6.1, we're dealing with the reciprocal, quotient, and Pythagorean identities. And so to start, a trigonometric identity. So that is a trigonometric equation that is true for all permissible values. That is very important. So it's true for all permissible values or allowed values of the variable in the expression on both sides of the equation. So we're going to be looking at equations, and all of your values have to work. So remember that allowed values, non-allowed values are where you're going to have undefined. So if we're looking, say, at the tangent function, your pi over 2 or 90 degrees, those ones all have undefined values. So those are examples of non-permissible values. And it has to be true all permissible values on both sides of the equation. So we're going to be looking at the three types here, which I've already stated. So our first one there is our reciprocal identities. And if you notice, they are literally the reciprocal. So 1 over sine of x is equal to the cosecant of x. Secant x is 1 over cos, and cotan is 1 over tan. You guys have already seen that. Hopefully nothing new. We're just putting a name onto them if you haven't given them a name yet. So number 2 is our quotient identities. Identities. Okay, so that's your tan of x, which we can rewrite as sine of x over cos of x, and cotan of x, which is cos divided by sine of x. All right. And the third one that we'll be studying in this lesson today is the Pythagorean identities. Would you guys believe me if I said I played around with this for an hour trying to really nail down my writing? Yeah, I wouldn't believe myself either. Okay, so and then these Pythagorean identities, these ones all come from your unit circle, which I have over here, and basically create a triangle using your a squared plus b squared is equal to c squared, and we come up with these wonderful, wonderful identities right here. So you have cos squared of theta plus sine squared theta is equal to 1. Cotan of squared theta plus 1 is equal to cosecant squared theta, and our other one is 1 plus tan squared theta is equal to secant squared theta. One thing that we can do is we can manipulate the equation, so you can, if you want to find out what sine squared of theta is, you can move cosine squared to the other side by subtracting, and you can do that for all of them to find different values, which we'll be looking at some examples of us playing around with it later, so it'll be cool. Alright, so we have already studied the reciprocal and quotient identities, as I just said, in the previous chapters, but we have not seen the Pythagorean identities yet. So if you care to know, this is how we get them. So I'm going to scroll on down here. So here we have cosine squared of theta plus sine squared of theta is equal to 1. So that comes directly from the Pythagorean theorem. Alright, so looking here at our wonderful unit circle here, we have this point here. If you remember that your x value here is your cosine of theta, and your y value here is your sine of theta. So you'd put in cosine squared plus sine squared is equal to, and if you guys remember what c squared is, in every kind of unit circle, your radius here is always 1. So then you put 1 squared, which is simply just 1. And then from there, you would just play around. You would use your reciprocal and quotient identities to get all these other different forms. So here for the cotan theta squared plus 1 is equal to cosecant squared theta. This one, we just divided everything by sine squared theta, and then we just simplified from there. And our third one, it was similar to the second one, but instead of dividing by sine squared of theta, we divided by cosine squared theta and then simplified. So if you're wondering what we can do with these identities, we can basically use these to simplify complex expressions that involve these trigonometric functions. We'll see these in later examples of this section, but for now we'll just move on to our next page, which is verifying trigonometric identities. So we'll flip the page there. So there are 2 ways that we can verify a trigonometric identity. Your first way is numerically through substitution. Oh. First way is numerically through substitution, and the second way is graphically using technology. Someday I will master this, it's great. Okay, so there's 2 ways we can verify, and just remember here, this little note here, verifying that 2 sides in an equation are equal for certain given values, or that they appear to be equal when graphed, is not sufficient to conclude that the equation is an identity, and it does not prove anything. So it doesn't prove anything. This is just verifying certain solutions. It looks okay, so we're pretty sure, but not entirely we can't say we're 100% sure until we actually prove it, which we'll be dealing with in a different section. Alright, so now let's look at an example. So here, our first one here, we need to verify a potential identity numerically and graphically. So for the first one, let's determine the non-permissible values in degrees for the equation. We have cosecant of theta is equal to cotan of theta divided by cosine of theta. And so remember, if you guys remember, your non-permissible values are basically any point where theta will make either side of the equation undefined. So that's where you have 0 in the denominator of any fraction. So normally, I guess it depends on which kind of functions you're given. If cosine, if that was in, say, the numerator, then we wouldn't have to worry about cosine because there's no values where cosine is undefined. But because it's in the denominator, and we can have a value where cosine is 0, so we need to look at, say, cosine of theta. When is that one equal to 0? Cotan of theta is also then we call the quotient identity, and that one can be written as a fraction, so that there itself we need to look for when is cotan of theta undefined. And then we also do need to look at cosecant theta, which is another reciprocal identity. So we need to look at actually all 3 of those to determine all of the non-permissible values for the equation. So first off, let's look at our first one here. Let's look at cosecant of theta. And if you guys remember, that is 1 over sine theta. So here we need to look at every time sine of theta is equal to 0. This will give us our non-permissible values for cosecant of theta. And you guys can use your unit circle if you guys remember. Every time that happens, we're either at 0 degrees, 180 degrees, 360 degrees, and so on. And it doesn't give us any restrictions, so we really should make a general solution here. So here we can say that for theta, for cosecant of theta, theta cannot equal, we could say 180 degrees plus 180 degrees n, if it looks like an n, where n is an element of integers. Okay, so that's for cosecant of theta. Our next one here, we're going to look at cotan of theta. If you guys remember that one is equal to cosine of theta divided by sine of theta. So we want to look once again at the bottom here. When is sine of theta equal to 0? We don't need to repeat this one because we already know from the first one when sine of theta is equal to 0. So don't need to repeat that one there. And so our third one there is cosine of theta. And we want to look at those values when that one is equal to 0. So cosine of theta, your theta values there when cosine is 0. That includes 90 degrees, 270 degrees, and so on. You guys keep adding 180 degrees. So for this one we can say theta cannot equal to 90 degrees plus or minus, or I guess you can just do the plus because your n value can be negative. And that'd be 180 degrees n, where n is an element of integers. Just going to scroll it down here a little bit. So what we should do is we need to make a generalized form of where we're combining what we found in each of our little samples here. So a generalized one that we can say here is that theta cannot equal. And generalized, if we look at, say, even just this third one here, where with cosine, here we're dealing with 90 degrees, then we go to 180 degrees, then we go to 270, 360, so we can make a generalization that this should be theta cannot equal 90 degrees plus 90 degrees n, where n is an element of integers. Okay, so if we add 90, we'll get 180, which is this one right here. 90 itself will be with your cosine of theta, and so on. So we should be familiar by now how to make a generalized solution for that. So just remember your non-permissible values are where your values of either equation will be undefined. Okay. So that was A. For B, we need to numerically verify that theta is equal to 45 degrees is a solution for the equation. So for this one, we simply just substitute those values in. Okay, so I'm going to write B here. Draw a nice little squiggly line there. You guys hopefully have more room than my monster writing on here. Alright, so here we need to put 45 degrees in for theta. So here we have cosecant of 45 degrees. And that is equal to your cotan of 45 degrees. Divide that by the cosine of 45 degrees. Alright, so using your chart there, you guys will know that cosecant is 1 over sine theta. So you take that sine value, which is, looking at our chart there, it's 1 over root 2, or you guys would know as root 2 over 2. And you just take the inverse of that, so it'd be 1 over sine of at 45 degrees is equal to cotan, which would be 1 over tan at 45 degrees, and then cosine at 45 degrees. Okay. Using your chart, this should be hopefully look a whole lot nicer here. So what we'll find out, that is 1 over root 2, or basically when you guys solve that out, it should be just root 2. That is equal to tan at 45 degrees is just 1, so we'll have 1 divided by, and cosine is 1 over root 2. Okay, I'm going to write this all the way over here now if you ladies don't mind. Okay, so now we have root 2, and is equal to, if you guys remember your fraction rules, you flip your fraction then multiply it. I'm sorry, that should be a positive 2. That was a mistake on my part. Okay, and then simplify. So we have root 2 is equal to root 2. Alright, and that is true there, so we can verify that cosecant of 45 degrees is equal to the cotan of 45 degrees divided by cosine of 45 degrees. Okay, so just remember that just verifies a point, it does not prove it whatsoever. So we'll move on to the next question. I'm just going to erase this top part here, and I'm also going to start a new video considering we're getting close to our 50-minute mark there, so you guys can load up video number 2 now.